So last time we finished with a statement of Lenz's law. So just as a quick verbal reminder, Lenz's law tells us what direction the induced EMF is when you have a changing magnetic field. So if, for example, you have a loop and there's a magnetic field passing through that loop, and this is not midterm material, and the magnitude of that magnetic field is increasing, then the induced EMF will be in a direction in the loop so that or to prevent the magnetic field from increasing. So it will produce a current, the EMF will be oriented in such a way that it produces a current that produces a magnetic field that opposes the magnetic field, the external magnetic field. So so let me just draw a picture here. You have your magnetic field, and here this is increasing in this direction. Then you have your loop. So if the magnetic field is increasing inside that loop of wire, that means that the flux is increasing. And so the Lenz's law basically tells us that the induced current will flow in a direction to oppose change in flux. So the current will act in such a way to produce a magnetic field that points downwards. And so what direction current would do that? Well, we can use the right-hand rule. So it is going around this way. So if we want to produce a magnetic field that's down, we would have to have the magnetic field or the current coming this way. So in this case, the magnetic field would circulate in that direction, and that's using Lenz's law. Now, just as a quick aside, sorry, I'm dying. Okay, I'm good. Just as a quick aside, the induced EMF doesn't always have to be the sole driver of the current, right? So let me write this down because this is important. The induced EMF don't always drive the current. And in fact, actually, the induced EMF can be opposite the direction of the current flow. And so the induced EMF can actually reduce the current flow in some circuit. But it's still true that the induced EMF tries to counter the change in flux. So let me give an example. So we have, this is the standard picture that we had before, where we have the bar, but this time we're introducing a battery into our picture and maybe a resistor. And then we have our bar that's moving, say, upwards with a magnetic field that's pointing into the screen. So in this case, if the bar were stationary, the current would just flow around the loop like that, right? However, the bar is not stationary. And in fact, because the bar isn't stationary, the flux through this loop, through the loop formed by the bar and the rest of the circuit, is increasing. And furthermore, you can check that it's positive. And the reason it's positive is because if we define the direction of current to be counterclockwise, which is what it is in this circuit, so it kind of makes sense, then the flux, or then from the right-hand rule, we know that the area vector points into the screen, and the magnetic field is also points into the screen. And so the flux is positive, and the magnitude of the magnetic field is increasing, so the flux is increasing. So it's greater than 0. So that means, so the flux is increasing through the circuit. So what does the what would the induced EMF do? It would act in a direction to counter that increase in flux. So if we wanted to counter that increase in flux, we can use the right-hand rule. Well, if the magnetic field is increasing into the screen, then we want to produce magnetic field that is out of the screen. So you would use the right-hand rule to establish that the EMF would try to produce a current that goes counterclockwise. So I'm going to, in blue, I'm going to do this. This is the I induced. Now, depending on what the EMF of this battery is, that induced current could be, that induced current could be larger, or sorry, that induced EMF could be larger or smaller than the clockwise current from the battery. And so what you would do is, say the battery had a very, very large EMF and the bar wasn't moving very quickly, then the current that would flow through, the actual current, the green current, would just be smaller by the amount equal to how much you would expect from the induced current. So in this case, this behaves like the following circuit. It would behave like a circuit that looks like this. So you have two batteries, and this battery is just the symbol for the induced EMF. This is the actual battery, and here's the resistor. So depending on how big the induced EMF is, which depends on the speed and the size of the magnetic field and so on, depending on how big the induced EMF is, either the current will just be forced through because the battery's EMF is too large, or it will actually cause reversal of the current. So that's what I mean when I say that the induced EMFs don't have to be in the same direction as the actual current flow, because you could have external sources of current effectively that that overtake the induced EMF and hence the induced current. So the induced current can just sometimes just acts to reduce the current flow through a system. Anyway, so right, so I have a little bit of a discussion of this in the lecture notes. I kind of proved this mathematically using the loop rule, but hopefully, but the idea is just to get the intuition across that the induced EMF doesn't have to be positive necessarily. Positive in the sense that typically we may write the induced EMF like this, but if the flux through the loop is increasing, this induced EMF would be negative, and so it behaves like a battery in the opposite direction. So you would have, rather than having a positive voltage here and a negative voltage here, you would have a positive voltage here and a negative voltage there. Anyway, so I talk about that in the lecture notes. I'm not going to spend a whole lot of time on it, though, because it's just a neat example. Right, so let's do another example. This is a fairly standard one that you'll see in a lot of physics courses, so it's worth doing. And this is the example of a conducting loop passing through a region with a constant magnetic field. I should write before I talk. Right, so the picture here is we have a loop in black. It's moving with some speed, say v, and it's entering a region with a constant magnetic field. Let's say it's into the board. It's going to enter the region, and then it's going to exit the region. So initially, there's no magnetic field before it enters the region. Then it's moving to the right, so it enters the magnetic field. There is something happens, then it's passing through the magnetic field, and for a time, the entire loop is inside the magnetic field, and then eventually it will leave the magnetic field region, and its magnetic field, the flux, will go back down to zero. So the question is how does the current in the loop, the induced current, behave? So we can approach this question at all three phases, entering, inside, and exiting, using two different methods. We can explain the phenomenon using motional EMF, i.e. you have some conductor that is moving in a magnetic field, and hence you would have some force on your charges. But you can also explain it using Lenz's law and Faraday's law. So initially, in this system, or at this moment in time when the loop is just entering the magnetic field, from the conceptual perspective of the motional EMF, you only have one side of your conductor that experiences a magnetic field. And so we can use the right-hand rule to find the force on charges in that right-hand side. And so we would establish using the right-hand rule. So the charges are moving at velocity v to the right, and then the magnetic field points into the screen. And so the force on positive charges would be up, the force on negative charges would be down. And so you end up with positive charges up here and negative charges down here. And in the rest of the circuit, there is no force. So while the charges can't flow directly back downwards because there's a force pushing them down, they can flow around the rest of the circuit. And so you would get clockwise or counterclockwise induced current. Now we could view this another way too. Let me actually do that in green. We could view this another way using Faraday's law and Lenz's law. So as the square of, as the loop passes into the magnetic field, the flux goes from 0 to not 0, and the amount of flux in it is increasing linearly because the amount of area of the loop that is passing over the magnetic field is increasing. So like at a later date, you'll have more area through which the magnetic field passes through. So in this case, the flux is increasing into the screen, right? And so the induced current will be in such a direction to reduce the flux that is passing through the loop. And so that would mean that it would try to produce a flux out of the screen. And so we can use the right-hand rule. We want to produce a flux out of the screen, would give us a current that is counterclockwise. And so obviously you get the same answer, which is a good check. And so hopefully you guys can see why you can, or how you can use both the concept of motional EMF and the concept of Faraday's or Lenz's law to explain this. Now, what about later on when the circuit or when the loop is, I don't know why it doesn't let me select the whole thing, when the loop is passing through? Let me paste, please. So at a later moment, we have something like this. Now it's just experiencing a constant magnetic field all the way through, still moving with the same speed or with some speed of v. So then the question is, okay, let's try it using motional EMF. So using motional EMF, we would find that the top bar, well, the top bar will have the top and bottom of the loop. They will experience a force separating the positive charges above and below, but that doesn't actually force the charges to flow in one direction or the other. So we could ignore the top bar and the bottom bar for now. So let's just think about the left and right bar. So on the right bar, you still have the right side moving to the right. And so you still have positive charges accumulating on one end and negative charges accumulating on the other end, the same as above. But here, we also have the right or the left side of the bar is also moving to the right at the same speed. And so you get the exact same amount of positive and negative charge separation on the other side. So now the charges can't flow around because the positive charges are repelled by the positive charges on the other side. Likewise, the negative charges are repelled by the negative charges on the other side. So here you have no current. We can view it using Faraday or Lenz's law too. Here, the flux through the magnetic field isn't changing. It's just moving at some speed. The flux, like it still has the same amount of magnetic field passing through it at any given instant in time. So there's no change in flux, hence there's no induced current. And so we can do this one more time, just looking at the case where it leaves the magnetic field. Hopefully by now you can guess the kind of arguments I'm about to make. I don't know why it keeps bringing up the keyboard whenever I try to paste. Very clearly using my fingers. Please let me drag you. There we go. So here, let's do it a little bit better. We have our magnetic field here. Again, moving with some speed v because it's just passing right through, I guess. Now, using the motional EMF argument, there's no motional EMF over here because it's outside of the magnetic field, but we establish a separation of charges on the left end for the same reason that there was a separation of charges on the left end while it was still in the magnetic field in the middle. And so you would have charge flow all the way around clockwise because there's no force preventing them from going that way, so they can meet up with their partner. Now, using Faraday or Lenz's law, the magnetic flux here, magnetic flux is still into the screen. You can kind of think of flux as directed in that sense. It's into the screen, but it's decreasing because the amount of magnetic field that overlaps with the loop is getting smaller. So the loop will try to induce a current that increases the magnetic flux in the into the screen to keep the flux the same. So using Lenz's law, if we want a magnetic flux, a magnetic field that points into the screen, we need to induce a current that is clockwise, and hence we get clockwise current flow, which again agrees with the motional EMF. So the arguments here are relatively straightforward, but the point is at least when you're talking about moving loops of charge or moving conductors, motional EMF is kind of equivalent to Faraday's law and Lenz's law. It's only once you start talking about things that aren't moving, things that are just changing in time, that you start running into more trouble. And in those cases, motional EMF just isn't a good explanation because nothing's physically moving. Instead, you just have to rely on Faraday's law and Lenz's law. So let's actually look at the ways that the flux through a loop, or the flux through a loop can change. So we know that the formula for the flux is just an integral over some surface S of the magnetic field dotted into the infinitesimal area, right? And so we can write this as an integral over S of the product of the magnitudes and the cosine of the angle between them, right? That's just a useful, that's just using the dot product. By the way, here, theta is the angle between A and B, just to keep things straightforward. So, oh, and by the way, this surface is bounded by some circuit, by some loop, right? So we can actually look at the rate of change of the flux as a formula. This is just the time derivative of this integral, right? So when could this possibly be non-zero? I.e., when could we have some changing flux and hence some induced current? Well, there are a few ways. One, if the rate of change of the magnitude of the magnetic field is not zero, then you could have that the changing flux could be zero. Now, by the way, all of these things don't necessarily don't force the change of flux to be non-zero, because it could be that one thing increases and another thing decreases it by precisely the same amount so that the net flux is still the same. But we're just looking at these in isolation for a moment. Another way that we could get a changing flux is if the angle between the area vector of the loop and the magnetic field is changing. So if you have a rotating loop in a constant magnetic field, that area is changing, or that angle is changing, so the flux is changing. Another way, if the integrating surface changes. So this one's a little bit less straightforward, but the idea is you're looking at the change in you're looking at what could change in this expression, right? So you could have the angle change, you could have the magnitude of the magnetic field change, but you could also have that the region you're integrating over is changing. Yeah, a shrinking loop, a moving loop. So for example, if the size changes, well, that would change the flux. Or if you have that the surface moves, like in the example we just talked about, in this case, the flux is changing because the surface is moving through a constant magnetic field. And then obviously any combination of these. Now, the point is you could have that, say, the rate of change of the angle is, or the angle is getting closer to 90 degrees, but the magnetic field is increasing. And so you could have a balancing act, like I said. But the point is these are kind of the independent ways that you could have a changing flux through some loop. And so in the lecture notes, I posted 4 examples of just calculating things like calculating EMFs, calculating induced currents, calculating magnetic fields, calculating rates of change, things like that. there's 4 examples that I noted in the lecture notes that you can go find. 2 of them are in the, or 1 of them is in the LibreText. 3 of them are in the Young and Friedman book. So I suggest you go check those out to get practice on calculating these sorts of practice on these sorts of problems where you might have to use Faraday's law or Lenz's law to learn something about a system. This would be things like, if you have a circular coil in a magnetic field that's changing with time, what is the induced current? Or if you have the, or if you put a magnetic field through a solenoid, what is the, or how does the, and the magnetic field is changing, how does the current in the solenoid change? Or if you have a coil of wire that's rotating in a constant magnetic field, what is the induced current? Things like that. Now, obviously, a lot of these problems are going to be problems where you figure out how the flux is changing and you figure out the induced current from that, or the induced EMF, but you can go the other way too. For example, if you know that the induced current is constant, you can learn things about the way the magnetic field is changing, for example. So just as a word of warning, that Faraday's law, Lenz's law goes both ways, right? It's an equality. The left side is equal to the right side. So it's not just if you know the right side, you know the left side. It's also if you know the left side, you know the right side. Anyway, for the rest of today's lecture, we're going to focus on consequences and applications of Faraday's law, Lenz's law, and so on. So there's a lot to go over. We probably won't get to all of it today, which is a bummer because we'll get something really neat at the end of lecture, but that'll have to be on Tuesday. Sorry, that'll have to be next week because exam. So the first thing to talk about are eddy currents. So we saw last lecture that in order for the bar to move down at a fixed speed, you had to apply a constant force downward, right? And the reason for that is because the charges want to move in a circular manner, so they're kind of bumping up against the top of the bar. And so from Newton's second law, Newton's third law, equal and opposite reactions, right? If the charges are applying a force upward, or if the bar is applying a force downwards on the charges to prevent them from moving up, that means that the charges are applying a force upwards on the bar. So in order to keep the bar moving at a fixed rate, you have to apply a force downwards, right? So the net force on the bar is 0. And so in that sense, the magnetic field that the bar is moving through kind of acts like a brake on the moving bar. And so I'm going to give a slightly more detailed example where you can see this happening. So, and this occurs in general, by the way. So for any conductor that's moving in a magnetic field, you'll generate small loops of current, right? Because the charges will want to move in loops. And depending on where those charges are that are moving in loops, the object might experience a current. Sorry, the object might experience a force. So let me give an example, which is also in the LibreText. It's a really good example. I like it a lot. So you have a pendulum. It's like rope or wire or whatever. And on the end, you have a conductor, like a large copper ball. So imagine for a moment that there's a magnetic field, say, here. Now, I'm actually going to make this a lot larger, a lot more cartoonish in scale, because I want to be able to draw this accurately. Come on, one more time. There we go. All right, so you have a magnetic field that's like in this region, say. The pendulum is swinging in and passes over this magnetic field. So it's swinging with some angular velocity omega is when it passes over that field. So the magnetic field is going to be perpendicular to the motion. So like initially it was oriented like this, and then it swung down, right? So initially it's swinging through, and the question is what happens to the conductor as it passes through the magnetic field? So we know that the charges that are, say, let me use green, or is blue smaller? No, blue's not smaller. It's whatever, it can be big. We know that the charges that are here, say a charge on the right side, it's currently moving to the left, and it will experience a magnetic field into the screen. Hold on. right? There we go. So it will experience a force downwards. A charge on the right hand, on the other hand, on the right side, on the other hand, is currently, and this is relative to the well, yeah. So a force on the right will also experience the same force. It'll experience a force downwards. Now, the kind of behavior that we'll expect near these, or like inside these loops, are really going to be circular motion around the edge, or like inside the region of this is very hard to erase, inside the region with the magnetic field. So what we'll see is we'll see something like this. So we knew that the force on the left was downwards and the force on the right was also downwards. So we'll see circular motion of these charges in these directions, because we know magnetic, or charges in a magnetic field, experience circular motion. So there will be a whole bunch of charges, you know, near the like inside the magnetic field that are circulating this way. So you'll have charges on the right half of the magnetic field will circulate clockwise or counterclockwise. Charges on the left half will circulate clockwise. So now the question is, what force do these magnetic fields, or what force do these I don't know why I'm blanking. What is the force that would be applied to these loops? So, or the force that would like if we can, they're not both counterclockwise, right? So perhaps let's think of them not as circuits. Let me blow this up a little bit, make it a little bit easier to picture. Right. So you have, imagine just a little circuit that's like halfway here. And these are just imaginary circuits, right? So when a circuit enters, it will feel a force this way. But once it's leaving, from Faraday's law, from Lenz's law, we can actually figure out based off of the flux, we could figure out what direction the current would flow in, the current through these imaginary loops. And it's the same argument that we have here. When you're entering the magnetic field, you have current flowing in one direction. When you're exiting the magnetic field, you have current flowing in the other direction. So here we'll have current flowing when it's exiting, we'll have current flowing clockwise, and when it's entering, we'll have current flowing counterclockwise. And you can use Faraday's law for that. And so then the question is, what force do these loops of current feel? And so we could actually just look. So on the right-hand side, the current, or the magnetic field, is 0. On the left-hand side, though, this is the left-hand side of the left, or of the rightmost loop. We can look at what direction, if the current is moving downwards in the magnetic field, we can look at the direction of the force. So V cross into the screen, the force is to the right. So the net force on that loop is rightward. Similarly, on the left, you also have the part that's in the magnetic field will experience a force to the right. And so the net force on these loops of current, these little swirls of charges moving around inside this conductor, they feel a force to the right, but they're not able to move to the right. They're not just able to leave the conductor. The conductor pushes back. So again, from Newton's third law, you feel this pendulum, we're looking at the velocity vector inside the magnetic fields. Let me use green to denote that. So here we have velocity vector here, we have velocity vector downwards. Because the velocity vector outside the magnetic fields don't matter, because the force depends on the velocity vector and the magnetic field. So if there's no magnetic field, like, yes, the velocity vector over here is up, but there's no magnetic field in that area. Yeah, so these are still mini circuits, right? And so those little mini imaginary circuits, those little swirls of current, they feel a net force to the right, which pushes the whole pendulum to the right. And so, in fact, as the pendulum swings through this region of magnetic field, it feels a force opposing the direction of motion. Now, so generally, these little swirls of current, these are called eddy currents. And eddy currents generally, let me put it on a different line. Eddy currents generally consume energy. And the reason we know that is so first of all, we know that these eddy currents are produced, and so they apply a net force to the right, which does, basically does negative work on the object, and so reduces the kinetic energy of the swinging pendulum. And so in that sense, it slows the pendulum down. Now the question is, where does that energy go? Well, these are actual physical charges moving through the conductor, and conductors have resistance. And so that that current that's flowing actually heats up the conductor as it passes through the magnetic field. So the energy the kinetic energy the pendulum had swinging down, some of it is taken away and converted to thermal energy of the system. And so these eddy currents, whenever an eddy current is present in any sort of resistive material, there will be current flow, and hence there will be resistance and hence energy loss. So eddy currents, for example, can cause braking. You can do magnetic braking, for example. But whenever eddy currents are present, they also cause heating, at least in conductors. And that's because conductors have non-zero resistance. So eddy currents are a really strange phenomenon, and they explain things like, why is it that if you drop a magnet through a copper tube, the magnet falls very, very slowly? It's because eddy currents are generated in the copper because the magnetic field is changing. And so those eddy currents produce magnetic fields that oppose the force of gravity on the magnet. I would do this demo, but I don't have the stuff for it. So for that, I apologize. This is one of those cases where teaching in person would be nice. Yeah, actually, maybe after lecture, like in a few minutes after lecture, I'll share my screen and I'll pull up like a demo of it because it's really surprising and very, very neat. Anyway, we'll get to that afterwards. Don't let me forget. Right, so another application. So that's one application of induced currents, right? So you can, for example, you can utilize eddy currents to like slow down things just by putting a magnetic field near a conducting thing. Kind of neat. What about electric generators? We've already talked about DC motors. They take in current and they turn them into work. But we can actually do the opposite. So with DC motors, we used current flowing through a loop to establish a dipole moment, and then that dipole moment experienced a torque due to an external magnetic field. And so we saw rotation. We were able to produce rotation using these brushes, a brush-full DC motor. Does the eddy convert kinetic energy to thermal at a 1-to-1 ratio, or is energy converted into other form? I can't. Yeah, I think it'd be a 1-to-1 ratio. I can't imagine any other way that it would be converted. I suppose you might be able to come up with some like strange examples where you can actually use the eddy current energy and then like convert it into electrical energy and store it. But I can't imagine anything that's not just like really contrived that would do that. Anyway, right. So we put current through a loop to produce a dipole moment, and then that dipole moment experiences a torque which causes the loop to rotate. So we can also do the reverse. So you can use motion of, say, a loop, and we can use magnetic induction. Maybe. Kevin, let's talk about that after lecture, because there might be more to say about that. So we use the motion of some loop and the magnetic induction that comes from the motion of that loop to produce, that's not words, to produce an EMF that drives a current. So in fact, unless you're on solar energy, unless you're on solar energy, this is where all of your electricity comes from. It comes from using the motion of something to produce an EMF which drives current, and that gets sent from the power plant to your house. And so a device that does this is called a dynamo, or more modernly, a generator. Dynamo sounds so much cooler though. So, right, so let's first talk about the first ever dynamo constructed. This was in the mid 1800s, I want to say, by Max, or by, what was his name? I want to say it was like George Faraday. That sounds right. Maybe, I don't think it was Max. Maybe it was John, I don't know. Michael, there you go. Thank you. Michael Faraday, that's right. Right, so Faraday actually constructed the first dynamo, the same Faraday who was responsible for Faraday's law. And so we can relatively easily analyze the system, actually. The first dynamo, it's hard to spell. The first dynamo was a spinning disk, a spinning conducting disk. And it's like a solid disk, not just like a ring. A spinning conducting disk in a perpendicular magnetic field. So one lead, so this is a dynamo, so it has to generate current, so that current has to leave somewhere and go into a circuit and then re-enter somewhere else. So one lead, or one contact, from the circuit is connected to the center, and the other is at the edge. So let me draw a picture for you. Right, so we have our, go away. We have a disk spinning, say that way, say with some angular speed omega. We have a magnetic field that's constant, that's passing through the disk. Now let's give that disk a radius r, and let's draw the rest of the circuit. So we would have a lead that comes in from the center and goes to do something else. Then we would also have a lead that's connected to, say, a brush, because the thing's spinning, so you don't want to just glue it. It has to just be connected. So this uses the same technology, by the way. It's the same brush full type of technology that you would need for a brush full motor. Right, so the question is why does this generate an EMF? So first imagine, instead of a disk, imagine you just had a rod that was rotating on an axis going around, passing through a magnetic field. This would be the same as if you just had a rod moving vertically, right? It wouldn't be identical, but what you would notice is that if you have a positive charge, say, in the middle, and it's moving, let's use the same direction as in the example that we're working with. So this is spinning around this way. If a positive charge is in the middle, it will feel, then it's moving with some velocity downwards. And so you can use the right-hand rule, V cross B, to find that the positive charges will actually feel a force to the right, and negative charges will feel a force to the left. And so all we're doing is we're just attaching a whole bunch of these rods together. It's a terrible drawing, I'm sorry. And so you can see why some positive charge, say here in the disk, is going to feel a force pulling it outwards, and a positive charge over here would feel a force pushing it upwards. Positive charge over here would feel a force pushing it outwards. Negative charge here would feel a force going to the center, and so on. So that's why a voltage difference will develop. That's why an EMF occurs, because you have charge separation, just like the motional EMF example. So the question then is how much motional EMF is generated? Right, we have the tools. We can actually go home and not go home. We can actually now calculate the amount, or like the voltage that you would get if it's spinning at such and such a speed and it has such and such a radius. So the way that we handle this is we're going to consider a small chunk of our rod, or a small chunk of our disk, rather, that takes up an angle d phi, has width, so we're going to consider this small chunk here, has width dr, and is located at position r away from the center. And the reason why we have to do this, the reason why we can't just do VBL like we did before, is because the velocity of each little chunk is different, right? Because it's moving at a fixed angular velocity, and so the speed on the outside is faster than the speed on the inside. So we have to actually figure out what the EMF is across just a little chunk and then add it all up. So we're going to add up all of these chunks, right? Because if the EMF at the center is, or if the voltage at the center is 0, then the voltage just outside the center would be a little bit bigger. And then the voltage in the next chunk would be that little bit bigger plus a little bit more, and so on. So it would add up all the way to the edge. So for a small chunk, so recall that for a rod moving at some fixed velocity, for a rod moving at speed v with length L, the EMF, the induced EMF, was VBL. So in this case, we're just going to use that, but just for our infinitesimal chunk. We get that the infinitesimal chunk of EMF is the speed of that chunk times the magnetic field passing through it times the length of that chunk. In this case, that length is dr, right? And it's the length perpendicular to the motion. So it has to be the dr, not r d phi. So now, if we just quickly remember our 9a, for circular motion, we have that the speed at any given point is equal to the distance from the center times the angular velocity, v equals r omega. Then we get the following. We get that the small amount of EMF that we add is v omega r dr. So the total generated, the total EMF between the center and the edge is just the integral, integrating from the center to the edge. So it's b omega r dr, or 1/2 b omega capital R squared. Bigger circles or bigger disks will have more EMF, but it's also harder to spin bigger disks. And so hopefully, as I already established, because you have positive charges that go to the outside and negative charges go towards the center, the edge of the disk is going to be the part of the disk that's a higher potential. And so you'll have current flowing this way, flowing from or flowing out the edge and then back into the center. So you might ask where this energy comes from. We typically have to reconcile energy conservation with whatever's happening. And we know that when you hook something up to a circuit, or when you hook up an EMF to a circuit, that circuit can use power from the EMF. It will like eat up some, it'll maybe charge a capacitor, maybe turn some of it into thermal energy from a resistor, whatever. So the question is, where does that energy come from? And it can really only come from one place. The only place it can come from is from the motion of the disk. That's the only reservoir of energy. So in order to keep a constant angular velocity, then, so by the way, this is just like the we just talked about something like this where oh yeah, like the rod that's moving downwards. You have to apply a force downwards to keep it moving at constant speed. To keep this disk spinning at constant angular velocity, we need to apply an external torque. And that torque is going to do work. And so the disk is a way, the spinning disk in the magnetic field converts externally applied work in the form of keeping this disk spinning at a constant rate into electrical energy, which is, I mean, modern power plants don't use this particular device, but they use something very similar. So in fact, this device is actually really interesting because you can use it to do something that's relatively modern. So in fact, we can generate electricity for free if we have an already spinning disk. Yeah, it's all steam engines except solar. That's because steam engines are very, very efficient. And so what could that possibly mean in our modern world? This is how hybrid vehicles work. This is how you get regenerative braking. So when you apply the brakes in a hybrid vehicle, what you're really doing is you're connecting your wheel up to external contacts, applying an external magnetic field, and that external magnetic field slows your wheels down, but also generates electricity and charges your batteries. So, without Faraday, there wouldn't be any Priuses or something like that. I mean, that's true for other reasons too. But yeah, so this is how regenerative braking works. Now, I'm sure that all of the fancy electrical engineers that work at Toyota and the other companies that have hybrids, I'm sure they've made this more efficient, made it more complicated to make it better. But this is the basic idea. And you can see that it's actually relatively straightforward how it works, how you can charge a battery by slowing down a spinning thing. Yeah, Faraday is responsible for Priuses. You heard it here first, folks. So another design that we could use to convert external work into electrical energy is just the DC motor in reverse. So here, and this is very, very hard to draw, so I will do my best, and I'm sorry. So we have our magnetic field, constant magnetic field. Maybe it's because you have two magnets. You have a north pole and a south pole over here. South pole and a north pole over here. I'm going to do my best to draw this, but it's challenging. And so let's say that the thing I'm about to draw is supposed to be viewed like end on, but it's really hard to draw that because otherwise it'll just look like a line. So imagine for a moment that you have like this squarish loop that you're viewing kind of at end on. And so it's spinning this way. Let's use a different color. Let's use blue. So viewed, if this were viewed properly, you would have, if my hand is the loop, it's spinning like this. And so you're just like somebody else is like it's a water wheel that's making it spin or something like that. But it's spinning with some fixed velocity omega. So then we hook up that loop to some things that are connected to brushes. Here's brush 1. Here's brush 2. And maybe rather than having a battery now, I don't know why my loop is so floppy, but rather than having a battery, now you just have a loop, or now you just have some circuit, like a resistor, or maybe it's a light bulb or something. And so the question is well, this loop is this would actually produce DC current because there's brushes. This is just a brushless or a brush full motor in reverse. But the idea is that when the loop is flat in the magnetic field, so magnetic field's running this way, the flux is 0. But as the loop turns, now the flux is increasing because it's not perpendicular anymore. And so the flux starts to increase. And so Faraday's law and Lenz's law tells us that the flux starts to increase. I'm trying to draw this. Flux starts to increase this way. So the induced current will be in such a way to counteract that. So it will produce a current this way. And so from the right-hand rule, it will produce the current that is so hard to draw. Sorry. Yeah, it will produce a current that ends up going. Let me not use blue for that. And I challenge you all to figure out, to check this at home on your own, but it'll produce a current that ends up going this way. And in fact, it'll always produce a current that's going that way because of the brushes. So all you're doing is you're converting a rotating loop, which maybe that loop is connected to a water wheel or it's connected to a steam engine or something that can rotate this loop. And then that loop is just connected to some wires. And those wires now all of a sudden have electricity because there's current flowing through them from this loop. Now, the difference between the example, is it just me or would it be easier to visualize if Sam uses? Well, so I'm trying to make it so it looks like I would have to reverse my video feed is what it boils down to. And if I did that, it confuses me a lot. So that's why I don't do that. Hence I use my, well, it looks like my right hand for you guys, right? Anyway, so unlike the above case where the EMF is constant as long as the speed is constant, in this case, it's not. So let's ask the question, oops. If omega is constant, what is the induced EMF? So in order to find the induced EMF, we need to figure out what the flux is. So when the loop is perpendicular to the B field, the magnitude of the flux is just the magnetic field times the area, right? When the loop is parallel, we get that the flux is 0. So in general, we can actually generalize this to figure out how the flux changes with the angle. So generally, if theta is the angle between A, the area vector, and the magnetic field, then the flux is just BA times cosine of theta. So the thing to note here is that the angle that the area vector makes with the magnetic field is changing at the same rate that the loop is spinning, right? Which means that the rate of change of the angle is just omega, which is the fixed speed that it's rotating at. So we can use this to compute the EMF. The magnitude of the EMF is the magnitude of the rate of change of the flux. We already know what the formula is for the flux. A and B aren't changing. The only thing that's changing is the angle. And so we can evaluate this derivative using the product rule. Sorry, the chain rule. So this is BA times negative sine d theta dt, which is just can be simplified to BA omega times the absolute value of the sine of theta. And so as I already established, to determine the direction of the current flow, we can think about this using Lenz's law. So when B and A point in the same direction, the flux immediately starts to decrease, right? So initially, say in this picture, say A is pointing to the right. As it continues spinning, the flux starts to decrease because now they're not pointing in the same direction anymore. So the EMF is induced to produce a current that circulates to increase the flux in that direction, which would cause circulation as described or as I noted in the diagram. So the circulation through the loop is always the same direction, and it actually flips. Like the circulation when the circulation, the orientation of the circulation of the loop stays consistent with the direction of the area vector. But because we have these brushes, even though the circulation changes directions, the direction of the current in the circuit stays the same because these brushes are always attached to this or because the brushes are also changing which part they're touching. This would be a lot easier if I could show you like some sort of 3D animation, but you know, we don't live in 2050, unfortunately. So I urge you guys to think about this particular example yourself. Make sure that the direction of current flow groks with your mental model, because it's very, very, very easy to mess these things up. But the important part about this calculation is that the EMF that it produces isn't constant, right? So when the angle between the two vectors is 0, you have no EMF. And when the angle between the two vectors is 90 degrees, you have maximal EMF. So actually what you end up with is you end up with an EMF that looks like this. And so this is kind of, or this is great, but it's not particularly useful, at least not for modern electronics. For modern electronics, well, okay, for modern electronics, we actually have AC that's routed from power plants. So we wouldn't even have the brushes here. We would just have an EMF that goes like this, right? But if you were to build this device, if you wanted a constant EMF, well, this isn't it. So in fact, what you would have to do is you'd have to use something to smooth out that EMF. So when the EMF is high, you would want it to reduce the EMF. When the EMF is low, you would want it to increase the EMF. So what could you do? Well, if you really wanted to make that correct, you would just put a capacitor there. So when the EMF is high, it charges the capacitor. And when the EMF gets low, the capacitor being charged has a higher voltage. So the capacitor helps out a little bit. And in fact, this is how you can smooth out non-constant voltages, non-constant EMFs. Just a little bit of some circuits analysis for you guys to think about. Now, just as a quick aside, in a DC motor, like not a generator like this, but in a DC motor, when you spin the loop of wire in the magnetic field, which you're doing because there's an induced torque, because the loop is spinning, it also induces current, which it induces its own current, right? Something that would oppose the change in flux. And so actually this induced current reduces the current that you put in. So it uses up some of the current. That's why a DC motor actually requires energy in a sense, because there's this effect that acts to slow it down unless you provide more and more energy. And so that induced current that opposes the current you're already providing, that's called back EMF. You'll hear that phrase a lot. Back EMF is just when the kind of. That's why the back EMF is the type of current that is the current that opposes the incoming current, because it's trying to change, because that incoming current affects the flux through the circuit. Right. So that's just a little bit of an aside. And so similarly, in a generator, the current in the wire produces a torque. So in the generator, the induced current produces its own magnetic field, and that magnetic field produces a torque inside or between these two magnets. And so the net effect here is that the magnetic field is that the external magnetic field will act to oppose the rotation. Sorry, the induced magnetic field will act to oppose the rotation of the spinning wire. And that's why you have to keep applying torque to keep it moving. So it doesn't just spin forever and you get free electricity. The induced magnetic field opposes the rotation. It's kind of like an eddy current almost, actually. Not quite, but it's almost like an eddy current. And so that's why you have to apply a torque, and that's why it takes work to generate this electricity. By the way, there is a good example of this in Young and Friedman that I linked to, computing things using these sorts of concepts to compute. So I would suggest you take a look at those too. They're linked in the lecture notes. So there's two more things to talk about, I think. And unfortunately, it doesn't look like we probably won't get to the last one, which is probably the coolest, or the most brain melting part, which would have been the most brain melting part of today's lecture. Unfortunate, but we have to get there. I don't know. Actually, this next thing is kind of cool too. So when we were first talking about magnets, or maybe it was in the middle, we introduced this notion of ferromagnetism, where you have all the little dipoles in the magnet lining up to produce a macroscopic magnetic field. This is how you make permanent magnets. And we also introduced this notion of paramagnetism, which is you have the dipoles aren't lined up, but they're kind of free to wiggle around. So if you apply an external magnetic field, the material produces more of that magnetic field because of that external magnetic field forces those little dipoles to line up. So it induces temporary magnetism. There's a third type of magnetism that we haven't talked about, and that's diamagnetism. So if you have a magnetic field that is changing, an external magnetic field that is changing, induces eddy currents in any material, really. It's actually literally every type of material. And it induces eddy currents for the reason that we just talked about. And so those eddy currents, like the eddy current that we kind of talked about in this generator example, those eddy currents are induced in a direction to oppose the change in the magnetic field. So if the magnetic field is increasing through the material, the eddy currents will be in the direction that is required to make the magnetic field smaller, to point in the opposite direction. They act to cancel out the change in the applied magnetic field. And this is via Lenz's law. Okay, so what does that amount to on a macroscopic scale? So this does include insulators, yes. Because they still have they still have just like how they still have dielectric constants, right? So the charges can still move a little bit. They just can't move. They just can't leave a region of their spot. But you can still have the little dipoles. You can have them rotating, which would be an eddy current. Right. So in most materials, especially most materials that are like insulators, the eddy currents that are produced, or the eddy currents that are the induced eddy currents, produce magnetic fields that are so small that they don't really have any noticeable effect. So this would be the induced magnetic field. Doesn't really affect the external magnetic field, i.e. it doesn't cancel it out or anything. It makes it just a teensy bit smaller. But in a lot of cases for normal size external magnetic fields, it's just not noticeable. But there are a few cases where it is. For example, water is very diamagnetic. Very is a relative term. So if you put a large external magnetic field on something, on a balloon filled with water, that a very, very large external magnetic field, the magnetic field that's produced, that's countering the magnetic field, the externally applied magnetic field, can be fairly substantial, large enough to, in fact, cancel out the externally applied magnetic field. And the end result here, this is just with water, is that you can float things. You can float things made of water in very, very large magnetic fields. Now, what things are made of water that I've mentioned? So I mentioned earlier in the course, frogs, right? So this is the common example. So if you go Google frog levitating in magnetic field, or look it up on YouTube, frogs and most living things are mostly made of water. You put a frog in a large enough magnetic field, it'll just levitate because water is very diamagnetic. It's kind of nifty, also very strange. Now, it's not useful. it was just a demonstration of a large magnetic field, but it's cool. So that's in insulators. Water is an insulator, right? Humans are a lot heavier. Also, we don't know how it will affect the brain, so different story, right? So that's in insulators. Water is an insulator, and so the eddy currents can't be very big. In conductors, the eddy currents are much larger, and so as long as the conductor isn't ferromagnetic or paramagnetic, you can actually observe diamagnetism, like in for example, I think copper is paramagnetic or not paramagnetic. In non-conducting or in non-paramagnetic conductors, you could actually observe this reduction of the external magnetic field. And there's a very special case of conductors. So let's talk about superconductors. So in superconductors, which have no resistance, like actually zero, why did my computer just shut off? That was weird. In superconductors, which have actually zero resistance, the eddy currents don't use energy. So in a conductor, by the way, these eddy currents will occur and they will partially cancel out the magnetic field, but those currents will slow down with time because there's resistance, and the current there's not really a like, if you take a conductor and take it from no magnetic field to constant magnetic field, in the time when you're turning the magnetic field on, there will be a large change in magnetic field, which induces eddy currents. But those eddy currents can't keep going forever because there's resistance. And once the flux through the material isn't changing anymore, once it's just sitting in the constant magnetic field, there's nothing keeping those currents going. But in superconductors, which do have zero resistance, the eddy currents can keep going forever. So they can cancel the magnetic fields forever. At least as long as the superconductor is a superconductor. And so the end result of this sort of phenomenon is, if you take a superconductor and you try to put it in a constant magnetic field, the magnetic field lines, like the magnetic field inside the superconductor, is just zero. There is no like the eddy currents 100% exactly cancel it out. And so if you were to draw this, you would have magnetic fields. Let's say your superconductor is a circle or a sphere. Your magnetic field lines, they would want to go through, but they don't. Instead, they just bend around. Magnetic field lines. And so what you actually observe, because the magnetic field lines can't get through the semiconductor, you actually observe a strong opposing force, i.e., or rather, you observe a strong force preventing it from moving. There are other deeper reasons as to why this happens, or other reasons why these things tend to like lock in place. That's called vortex locking. It's a quantum effect, and it's due to impurities in the semiconductor. And there's a further effect which doesn't involve changing magnetic fields at all. So this effect that we just mentioned, where you can levitate a superconductor by putting it into a magnetic field, that occurs because at the instant you're putting it in, the magnetic field changes, which induces these eddy currents. But if you create a semiconductor inside of a constant magnetic field, the magnetic field never changed for the entire time that object was becoming a superconductor. So the question is why that still happens. It still expels all magnetic fields from inside of it the moment it becomes a superconductor. And that effect, where it doesn't require changing magnetic fields in order to generate eddy currents, that effect is called the Meissner effect. And it cannot be explained using the material that we've covered in this course. It can only be explained using quantum mechanics, basically. It's really neat, though. Look up like Meissner effect floating superconductor, and you'll see that you can like skateboard on like a frozen piece of ceramic and levitate like it's a hoverboard, basically. No, you're not a superconductor, because even if you don't want magnetism, it still gets in you. Right, so we have 6 minutes left. I guess we'll start the discussion that I wanted to have. So that's superconductors. Superconductors are cool. And they're quite literally cool. They're all, significantly below room temperature. But there's another topic that we have to talk about that we won't have time to complete, and that's induced electric fields. So this is like kind of the biggest part of E&M, because up until now we've talked about how electric fields, or how moving charges, which are caused by electric fields, can produce magnetic fields. And we've talked, but we haven't really talked about how magnetic fields can produce electric fields. And there is sort of a duality here, so that should happen. So we can now explain it now that we know about magnetic induction. So first, I'm gonna introduce a paradox. So let's say that you place a long solenoid inside a loop of wire. A loop of wire. So the picture is like you have a loop of wire and then you have like a solenoid. And you have current flowing around the solenoid, right? So it's inside a loop of wire, and we vary the current flowing through the solenoid. So that would mean that the magnetic field inside the solenoid is changing, right? Because the magnetic field inside a long solenoid is proportional to the current. So as a quick observation, if you were to do this experiment, we see that a current is induced in the loop. And that follows with Faraday's law, right? But the magnetic field from the solenoid is 0 everywhere outside the loop. Sorry, everywhere outside the solenoid, including the magnetic field is 0 at the loop. So somehow you have this non-zero magnetic field, or you have this 0 magnetic field at the loop is somehow, like literally the magnetic field is 0 everywhere outside the solenoid. Somehow it's still affecting the loop. So the paradox is, how is it? How does the solenoid affect the loop? It's not a trick, actually. This is actually kind of hard to explain if you don't think about things too hard anyway. So to resolve the paradox, we kind of need to back up to earlier in the course, when we talked about the current flowing in a circuit. So what causes that current to flow? Well, the only way that charges are moving is because a force is acting on those charges. And if a force is acting on those charges, that means that there is an electric field that is present where those charges are, and that electric field applies a force. So a typical circuit with a battery would look like the following. This is like a blown up version where you can see the electric fields. So you have your battery, you have your positive side over here, your negative side over here, and then you have your conductors, which are just basically long tubes filled with electrons. So inside of the battery, you have a whole bunch of charges that are separated due to and they're separated by chemical reactions. And so those charges are separated and develop an electric field that runs from positive to negative. And also you have an electric field that runs around the circuit, and that's what causes current to flow. The electric field that runs around the circuit, right? Field vectors aren't supposed to turn. So Kirchhoff's loop rule is actually just a statement about fields. It's a statement about the electric field. I should finish that sentence. So Kirchhoff's loop rule, which says that the sum going around a loop of the change in voltage, that's 0, right? But we know how the voltage relates to the electric field. The voltage, or the change in voltage from one place to the other, is just the negative integral of the electric field going from place to place. That's because the electric field is the negative gradient of the voltage. So this is equal to an integral around the loop of E dot dl. So in this case, in the case above, there are two places that have different electric fields. The electric field is constant everywhere inside the conductor, and it's constant inside the battery, but they're potentially different values because, you know, they're different distances and so on. So in this case, we have that 0 is equal to an integral. Well, there's an integral over the electric field inside the battery of E dot dl, and there is an integral through the conductor of E dot dl. So, and you would find that those two things add up to 0, in part because the electric field through the battery is in the opposite direction from the path length for the that we're going around the loop. So you'll get a negative contribution from the battery and a positive contribution around the loop, and you can add up to 0. But what if there isn't a battery? What if the source of current flow, I'll be done in a minute, was an induced EMF? Then there's nothing to cancel out the EMF around the loop. Then there is no battery. And so our picture looks like this. Ooh, terrible. And so we just have electric field just running in a loop without any obvious battery. Now here there is maybe there's magnetic fields with magnitude decreasing in this direction, but there's no actual source of the electric field that can cancel out that EMF. So I'm almost done. So here, the loop rule says that if we were to take what we did above, the loop rule states that an integral around the loop of E dot dl is equal to 0. But this is wrong. It has to be wrong, because that would mean that the electric field is 0, which would imply that the current is 0. And we know that there is current flowing. So that formula has to be wrong. It cannot be the case that the electric field around a loop, or the integral of the electric field around a loop, is 0. Just can't be true. I'm going to leave you on the cliffhanger as to how we resolve this potential issue, and we will also resolve the solenoid paradox next lecture, or next time I'm lecturing. Right, so I